Math 1314, Tyler Junior College, Section 3.4, Zeros of Polynomial Functions. I kind of lied to you at the end of the previous video. I said this one would be the next example. But before we get to further examples of using the rational zero theorem to locate zeros of a function and hence find all the zeros, I want to introduce you to another tool that we can use to help us narrow down our list of possible rational zeros. Because so far our list has been fairly tame. I think the biggest one we've seen so far has only had 8 possible rational zeros. But I've seen problems where the list of possible rational zeros is 24, 36, 60. I mean, there's just a ridiculous number of possible rational zeros that you could generate. And so sometimes it's necessary to narrow that list down. Otherwise, we're in for a lot of synthetic divisions, many of which wouldn't work. One of those tools is called Descartes' rule of signs. Rene Descartes was a French mathematician, philosopher, amongst other things. One of his biggest contributions to math is the idea of being able to graph on a coordinate plane. So you can blame a French mathematician for that. As a philosopher, he's also noted for saying, "I think, therefore I am," which reminds me of a really nerdy, stupid joke. Remember, he's the one that said, "I think, therefore I am." Rene Descartes walks into a bar. The bartender asks, "Can I get you something?" He says, "I think not." Poof, and he vanishes in a puff of smoke. Think about it. Anyway, so what is Descartes' rule of signs? Well, suppose f of x is a polynomial function. Okay, we're dealing with a lot of those. Part A, the number of positive zeros, positive numbers that make this equal to 0, is either the number of sign changes in f of x, and I'll explain what I mean by a sign change in a minute, or that number minus an even number. Part B says the number of negative zeros is either the number of sign changes in f of negative x, or that number minus an even number. So in both cases, we're counting something, and we're saying it's this number or this minus an even number. So how does that work, and what do I mean by sign changes? Well, let's take a look at this function. Determine the possible number of positive and negative zeros of f of x equals x to the 5th plus 2x to the 4th plus 5x to the 3rd minus x squared minus x minus 1. In order to answer that using Descartes' rule of signs, we need to count sign changes. Now, what do I mean by sign changes? Let me rewrite this function real quick because I want to preserve the original one, but I also want to mark it up. So here's the function. By sign changes, I mean the number of times that the coefficient switches between being positive and being negative. So for example, as we move across, make note of the signs. This first coefficient is positive, as is the next. No sign change there. As is the next. No sign change there. However, as we go from the coefficient of x cubed to the coefficient of x squared, there is a sign change. It was positive, it changed to negative. And if you notice, that is the only sign change in this entire function. Positive, positive, positive change, negative, negative, negative. Because there is one sign change in the original function, that means that there is one positive zero. One positive number that makes the function equal to 0. That doesn't tell us what it is. It just says there is one. Now, concerning the or that number minus an even number, well, I can't subtract an even number from this because it will become negative, and since we're counting things, we don't count with negative numbers. Now, by contrast, for part B, we do the same thing except we put in negative x, which isn't nearly as bad as it seems. You just have to remember that when you raise a negative to an odd power, it stays negative. But when you raise a negative to an even power, it reverts to being positive. So what that means is when we substitute negative x, all the even powers signs will stay the same, but the odd power signs will change. So we just have to change the odd powers, coefficients, signs. The odd powers, coefficient signs. So x to the fifth is an odd power, it's going to change to negative x to the fifth. X to the fourth is an even power, it's going to stay the same. So it will stay positive 2x to the fourth. X to the third is an odd power, so it will change to negative 5x to the third. X squared is an even power, it will not change, it will stay negative. X to the first is an odd power, it will change, so it'll change to positive. And the constant term doesn't care what the x is doing, it's not going to change, it stays the same. Now let's count sign changes. Doesn't take long. There's one, there's another, no, there's another, and there's another. So we got a total of 4 sign changes in f of negative x. Remember, we're counting negative zeros. So that means there are 4 negative zeros or this minus an even number. If we subtract 2, 4 minus 2 is 2. So maybe there's 2 negative zeros. Or if we subtract a bigger even number, or equivalently subtract 2 again, there could be 0 negative zeros. So how is this information useful? Well, if I had a list of possible rational zeros and I knew that one of the zeros is positive, I would start there. Now be careful. This doesn't say one positive rational zero, it just says one positive zero. There are positive numbers that are not rational. For example, 3 plus the square root of 2. That's positive, but you won't find it in the list of rational numbers. It's irrational. Or even 3 minus the square root of 2 for that matter, both of those are positive. So this doesn't mean in your list of possible rational zeros, one of the positive ones must work. It just says one of the positive ones could work. Similarly, 4, 2, or 0 negative. Now how is this useful? Well, if we ran across a negative 0, then there must be at least one more, because we can't just have one negative 0. In the next video, which will be an example of finding more zeros of functions, we will use Descartes' rule of signs to help us make decisions about what numbers to try. Oh, and for the record, you can do all of these problems without using Descartes' rule of signs. It's just another tool for helping us narrow down our list of possible rational zeros.